Well, welcome and thank you for joining us. I'm Guillermo Varela from McNeil Europe, and I want to introduce today's speaker, Boyan Mihaylov. He's a computational designer and CAD specialist at Joris Laarman Studio. Coming from a background in architecture, he specialized in parametric modeling for digital fabrication during his projects with ICD at the University of Stuttgart. In the last years, he has been working on the digital implementation of complex designs in various scales, looking for innovative computational solutions for design problems. Today, he's going to show some typical approaches for algorithmic modeling used in the designs of Joris Laarman Studio's products, illustrating how they relate to their design philosophy and visual language. Special focus will be placed on the parametric techniques behind several large-scale 3D-printed metal structures produced by MX3D. Please remember that you can ask questions in the chat and we can answer them in the last 15 minutes of the webinar. Also, the webinar is being recorded and we will upload it to YouTube tomorrow. Thank you again, Boyan, for accepting our invitation, and please start with the presentation if you're ready.
Well, thank you very much, Guillermo, for this introduction. And yeah, I have to say that I'm very pleased to deliver this talk to the Rhino community as a Rhino user myself. And I know there are Rhino users of many different types amongst the audience. So I have tried to prepare this webinar to both provide inspiration or satisfy the curiosity of the people who have come here to hear about Joris Laarman Studio and our projects, but also on the other hand to share some knowledge and my perspective with the more technical oriented minds among you. And so I have structured this presentation in 3 parts essentially. First, I will give an introduction of our studio's practice and our design philosophy and some of the notable projects that relate to it. Then I will provide somewhat general overview of our design workflow and how Rhino and Grasshopper fit within it. And finally, I will dive deeper into this one specific design technique that we have used for some of our largest scale steel printed objects, which are all produced by MX3D. And for this, I'm going to eventually show a snapshot of a Grasshopper definition for very quick demonstration of these techniques that I'll mention. And I want to note here that I will, throughout the presentation, I will be mentioning not only projects where I have personally been involved, but also such where the studio has worked with many wonderful experts and minds that are professionals in Rhino or other otherwise algorithmic modeling techniques. Unfortunately, for lack of time, I won't be able to explicitly credit all of them, but it should be known that our studio is always very open for fruitful collaborations with any kind of technically competent and innovative people. So without further ado, Guillermo already mentioned, my name is Boyan Mihaylov, and I work as a CAD specialist and a computational designer at Joris Laarman Studio, which is a practice established by Joris Laarman and Anita Starr back in 2004, which deals with the design and manufacture of objects of different scales that are connected to different visionary narratives that reflect the technological shifts of the digital revolution in a way that connects past and future. So, coming from a generation that has witnessed the transition from the pre-internet world to this ever-accelerating information age of today, Joris's aim is to bridge the gap between the past physical reality of craftsmanship, patience, contact to material, and connectedness to nature, to this exciting future of advanced technology, which is essentially a future world deeply marked by the digital realm in which virtually anything is possible. And this kind of bridge between future and past enables craftsmanship to evolve to a new relationship with technology by not being replaced by it, but by being augmented by it in ways that haven't been possible before. And on the other hand, this bridge connects high-end technology to the physical roots that some might say it tends to move away from. And this so-called bits and craft design philosophy is well illustrated, for example, in our Maker series, where we have prototypical shapes of chairs, tables, and benches that get digitally discretized into different patterns to become physically built in a wide range of material systems. On one hand, these patterns carry certain aesthetic references to a visual language of the digital, of the future. And on the other hand, breaking down these shapes into these patterns enable the products to be manufactured by hand, by being broken down into manageable pieces. And in this time of an emerging digital maker culture, where end users have access to small CNC machines more and more, anyone with a 3D model is able to materialize the final product. And this was the idea behind this spin-off project of the Maker series, this puzzle chair, where the 3D model has been put available as open source. So while the Maker series deal with different types of discretization of digital shapes, you probably have seen that 3D printing has been playing an important role in our projects. Obviously, because of its promise of a seamless, precise, and streamlined fabrication of complex geometries. And this allows for the creation of adaptive structural gradients on various different scales, up to a very fine, almost microstructural scale, which is exhibited in our both in our gradient aluminum chair and our adaptation chair. These smooth transformations in scale, density, and detail over the global structure of an object can be combined with certain discretely integrated tectonic principles that can allow the production of objects much larger than the actual build volume of a 3D printer, such as, for instance, this gradient lounge chair. And in this project, where I was quite closely involved, there was quite an intense collaboration between craftsmen and the machine, because great amounts of care were put in the assembly of the 3D printed parts and the finishing of the seat, including the CNC knitted upholstery, which had to be attached to the structure of the chair through customized 3D printed connectors. However, in order to truly break the spatial boundaries of the machine and the 3D printer, we explored a series of works that led to the development of a metal 3D printing technology and the establishment of our daughter company MX3D, which is currently an important player in the industry of WAM, or wire arc additive manufacturing. This technology makes very large objects possible in very durable and structurally strong materials, such as stainless steel, aluminum, and bronze, and obviously in a very large scale, up to an architectural scale, as can be illustrated by the MX3D bridge project, which I'll talk about more a little bit further. 3D printing naturally is becoming a state-of-the-art technology nowadays. Our focus, the focus of our works, is also expanding towards other future narratives that are relevant for the environmental issues that society is facing. And coming back to the context of connecting past and future, this means connecting technology and culture back to nature. So as technology sometimes seems to create a certain culture of separation from nature, the challenge is to reverse this relationship by applying the advanced digital toolset we have to promoting biodiversity, reintegration of living organisms in our everyday life, and working with materials that have a reduced carbon footprint, and managing, of course, the unpredictability of certain of such organic materials and their behavior. Now I'll talk a little bit more about our design approach, coming back to the relationship between culture and nature. One could say that the visual language of most of our products is somehow marked by forms that could be categorized as biomorph or organic looking. And this partly relates to the structural intelligence that can be found in natural systems that we sometimes use as inspiration for our designs. As you can see on the left, this is our so-called bone chair, which is topologically optimized, inspired by the development, the growth of tree branches and the structure of bones. And other times, it's the cultural significance of the abstraction of natural form as an ornament, as can be seen in many schools of art and design. But in any case, an overarching aspect that is quite often present in our projects is the continuous flow of the form and its gradient differentiated structural consistency, very much like an organically grown natural tissue that adapts to certain situations. Now, the digital design tools we use allow for almost unlimited freedom of expression by exploiting algorithms that in one way or another mimic interactions happening in natural processes. So we use such algorithms in our workflow, and we conceive the shape of an object first in the digital realm under some consideration, of course, of structural and ergonomic requirements. And this shape generated in the digital realm becomes the main guide for the materialization. The materialization usually happens through a series of experiments and mock-ups and material tests until an appropriate fabrication process is found, which potentially informs back some optimization steps in the digital design as a feedback loop before the final production of the piece. We use predominantly Rhino and Grasshopper in our workflow. To me personally, as a CAD specialist, they're a Swiss Army knife of a software that combines geometric precision with a lot of versatility, not only in the visual expression that they enable, but also in the capabilities for managing design processes in many different ways and customizing these workflows. That's, of course, all thanks to the light and expandable and community-driven nature of the software. So that's why I'll go a little bit more into detail on how Rhino and Grasshopper fit in our studio's workflow and in my personal workflow as well. A typical project at our studio starts usually with an ideation phase, which is either based on a commission of a product from one of our series, for which a new iteration needs to be made, or an exploration of some new ideas that are aligned with our design agenda. Oftentimes, Joris comes with a sketch image or some kind of narrative that needs to be developed into a geometry and eventually into a product. And a very interesting aspect of my job is finding and fine-tuning the right algorithm that can generate the desired shapes and patterns. Sometimes it's a more mathematically, geometrically deterministic algorithm of geometric constructions, and other times it's a more unpredictable, emergent, nature-inspired algorithm, which is good for exploration, but we can only turn it into a design tool with the right degree of control embedded in it. So in the early stage, when an idea still hasn't found its shape, I can use such algorithmic form-finding techniques with rather unexpected behavior in order to get inspiration or produce variants that we could, that we could get ideas from. But in many cases, especially in the later stages, there is a very particular image pursued by Joris, for which I need to embed many layers of control to guide the shape into its desired configuration, while still, of course, preserving the emergent quality of the computational approach. On one hand, there is, of course, the pursuit for a natural look, which is rooted in our admiration for natural forms. This natural look can be enabled by the complex algorithms of today's technology. But on the other hand, there is the artistic abstraction of the natural form, the deliberate craft of the designer that reflects cultural context and human individuality. So therefore, the challenge is to find the right balance between design intent and intrinsic logic of the form-finding processes. So we need to find a balance between a controlled look and an emergent behavior, or in other words, as you probably know, the well-known dichotomy of chaos and order, which is ever so present in many in the artistic practice. My personal approach is to construct designs bottom up, creating shape building processes instead of finalized shapes. And often this means translating Joris's notions of sculptural logic into a mathematical one, basically a logical sequence of geometric operations that form the desired shapes. This is also quite an interesting element of my daily work, since it allows me to dissect certain aesthetic notions that come from Joris's sculptural language and represent them as harmonies of numbers, equations, and geometric relationships. For instance, a certain aesthetic input can be that the form should flow in a certain way, or exhibit certain visual tension, or contain details of contrasting size in different areas. And such notions require a careful choice of procedures and algorithms to produce the exact desired effect. Sometimes, of course, the design intent is so specific that some less procedural modeling is involved, such as sub-D editing, which is basically the equivalent of a sculptural approach in Rhino. And this is either done by Joris or by myself or by someone else on our design team usually to get a suitable guide shape for a design. But this guide shape still undergoes a lot of manipulation through Grasshopper to become a producible object. I usually operate on one single parametric model for a specific design, which takes minimal to non-static input from Rhino and incorporates all kinds of different steps from the generation process, from the design process, such as the fabrication parameters, the structural details, the calculation of material quantities. From this master model, we can also extract data for the fabrication processes. And since we mostly work on product scale, on a small furniture scale, that's okay. But in some cases, some more complex projects, such as the MX3D bridge, the Grasshopper definitions sometimes almost reach the level of a small BIM model, which always allows the dynamic changes of parameters all the way back of the initial guide geometry that can propagate themselves back to the forth to the fabrication model. After the final configuration of the design parameters is fixed and the shape is fixed, so to say, the fabrication data is exported accordingly to the different fabrication processes. And the process continues either in our own in-house workshop with our available CNC machinery, or via certain external manufacturers. And at the very end, it reaches the careful touch of the many perfectionist handworkers that work in our studio, and they are the ones that really bring the amazing detail and quality of the finished product. Sometimes data from the physical world can provide feedback to the digital model via 3D scan models. And that's, for instance, either to capture specific side characteristics, as you can see on the example of the bridge, or to identify certain deviations between the digital model and the produced physical artifact. For example, when certain warping has occurred during the 3D printing process and needs to be manually adjusted. Recently, we also started implementing AR technology in various steps of our workflow. We use the Hologram plugin together with the Microsoft HoloLens. On one hand, to augment fabrication processes, but also during the design phase to create intuitive design interfaces away from the office desk, where one could almost literally sculpt in mid-air, or simply to present designs in a real-world context and get a better grasp of their scale. Which is really helpful in the creative workflow. For the next part of this presentation, I will guide you through a typical parametric workflow that I use in Grasshopper. And it is not necessarily linked to one specific project by our studio, but rather synthesizes some algorithmic approaches that come up in a series of our works. For this, I chose a design strategy that is used, as I said, in multiple large-scale metal printed projects, all produced by MX3D. These are the MX3D bridge, the gradient screens, and the Oregon bench. But some of these techniques can be traced back to older projects or are still being used in my personal workflow sometimes. In any case, they demonstrate some key aspects of our design language and or at least my approach to interpreting it. And I will first elaborate a bit on the projects, the specific projects, which are the context in which these techniques were developed. First of all, the topics of gradients is very central to many of our works. We work with geometric systems that exhibit local variation or transformation throughout the general shape. As outlined before, such principles can be observed in nature when you think about differentiation of cells, physical tensions on fabrics and tissues. And such principles have also established themselves somehow as part of the visual language of the digital age, since they they're sort of a demonstration of the mass customization paradigm as opposed to the mass standardization of the industrial age. And obviously the advanced representation algorithms that we have now are also contribute to them becoming such part of this digital visual language. Mathematically, a gradient can be described as the gradual change of a numerical value over space or time by having a domain from between a starting value and an end value and a parameter that indicates the change along this domain. One could represent almost the vast majority of geometric procedures that are used in our designs. As I mentioned earlier, the interplay between sculptural and geometrically constructive approaches lies at the foundation of many of our works. Some of the early editions that started the metal printing technology were the so-called dragon benches, where first of all, the base shape is modeled as a sub-D following a very specific sculptural logic of motion and curvature. And subsequently, this guide shape is populated with a large scale gradient in the form of a structural diamond lattice. The adaptability of the lattice's gradient to the curvature becomes a very important factor here, since it allows essential regions, for example, the highly curved regions, to be more reinforced through local densification, and other regions, for instance, at the back seat, to be opened up. After the first dragon benches, the metal printing technique quickly advanced in its capabilities. So from producing single line lattices, it evolved to enabling complex double curved surfaces. And ultimately, we were able to create a surface continuum that spans between both, from solid structural members and surfaces to an open mesh, like a true differentiated structural skin. And such a geometric system finds many more layers of implementation of the gradient principle that I described. During the MX3D project, we wanted to examine the potential of such a structural adaptivity of the gradient skin. So we looked back at our topologically optimized bone chair and asked ourselves, how can we do something similar? How can we make a differentiated structure that adapts to the stress distribution in the hull of the bridge? So we started with an organically curving envelope shape, a form that could integrate on one hand within the context of De Wallen in Amsterdam, with its very eclectical, hedonistic environment. And on the other hand, like such a curved shape would allow us to push the limits of the 3D printing technology to sort of demonstrate its full potential. For the structural inspiration, we worked closely with structural engineers from Arup, who provided us with a stress line model generated with the plugin Karamba. So essentially, what they did is they took certain speculative load scenarios and potential anchor points of the bridge, and through this bridge envelope, they could see how the forces of tension and compression concentrate in certain regions of the geometry. And then these fields of concentrations and line concentrations were used as the attractor basins for the densification of the actual structural mesh of the bridge. So you can see that in close proximity to the red lines, we get thick structural members that then slowly open up into a permeable mesh. This principle was later on further applied to our gradient screen series, which were sort of meant as a prototypical study of how the morphing skin could spread vertically and form the enclosure, for instance, of a building or a facade, for example. So these objects were designed both as sculptural room dividers for clients, but at the same time as speculative cutouts from a much larger structure that you could imagine continuing. The profile shape of the double layered skin of the gradient screens was carefully defined following many aesthetically driven constraints. We had to have contrast between different thicknesses, a dynamic of the shape that invokes impressions of tension, draping effect that makes this very solid skin to appear more light as a textile. But also, of course, there were structural constraints assuring the piece stands firmly on the ground without toppling, taking into account material warping and overhangs during the 3D printing, additional stabilizing structure in between the layers, etc. A big challenge was how to define this elaborate shape and these with all the effects of the profile shape in a robust way as algorithmic logic. And this had a lot to do with the mapping of vertex offsets through different kinds of layered mathematical functions. So we can view this profile shape as the result of many different mathematical functions overlaid over each other. And this provided much quicker results and much more strategic results than actual, for instance, cloth simulations or any other physical driven simulations, since they enabled a much more strategic control over every little fold of the skin. And in a way, this also highlights the notions of this ever-present search of visual harmony through mathematical harmony, which is something that can be traced back through many schools of art and design. Eventually, the gradient skin principle made a full circle by being fed back to the very first typology that started the metal printing journey, the Dragon Bench. And namely in this latest iteration that was done for the Nike headquarters in Oregon, this time with a much more powerful structural adaptivity and more expressive visual language. It really manifested the idea of the dragon skin much more concretely. I will now walk you through a demonstration of the specific aspects of the gradient skin technique in Grasshopper. And to simplify things, I have taken, I won't take any of the geometries we used in the previously mentioned projects, but rather a new primitive typology that I just prepared for this webinar. It's a column or a vertical enclosure or a tower, if you like, something basically with a straightforward direction and easily tweakable parameters. If you want, you can view it as an element of a bigger structure, as some kind of a support, or as the larger structure itself, from which some interesting segments can be extracted to produce room dividers or screens. So usually the first step is to create a rough guide geometry. And I know there's two kinds of people. There's the people who prefer breps and surfaces and those who work more with meshes. Breps and surfaces are, well, I mean, here we go into the more technical part, I guess. They're very good for their smoothness and the Boolean operations that can be done with them. But I personally prefer to work with meshes rather than NURBS, since they give me more explicit control over defining the positions of the vertices using different functions. And of course, this brings with itself much more complexity in the management of mesh topology and Grasshopper data. But throughout time, I have learned to incorporate a certain set of geometric techniques to facilitate this. Something worth mentioning is that we also have sub-Ds, which are a relatively new implementation since Rhino 7, and they're a wonderful thing since they combine the best of both worlds of surfaces and meshes. They can be translated into both, into either geometry. So it's something that we always like working with. To create the initial mesh and subsequently the sub-D geometry, I use constructions of curves and points. So here we have like a typical twisted tower situation, which consists of two rotated polygons, in this case triangles, connected by blend curves. And here already I define the ending of the structure because it greatly affects the dynamics of the shape by trimming or shortening these blend curves with using a single graph mapper, which in a way allows me to modify all three curves simultaneously without explicitly having a single slider for either of them, for each of them. And that it does it in this harmonic way. As a next step, the blend curves are discretized with points and a mesh is fit through these points. And since from this mesh, I will then create the smooth sub-D geometry, I want to be able to take a break and bake it and edit certain details of the sub-D manually. So it is very essential to have just enough control points to define the shape well enough without losing detail, but not too many as to make the manual editing process too tedious. So I use one subdivision iteration through a Weaver bird component and can potentially bake the sub-D, go back to Rhino and create, for instance, create certain moments of tension in the shape if something wasn't done right by the algorithm. And this can also be done by Joris or whoever else is collaborating on the model. There's a lot of attention to detail in the dynamics of the shape. And then it can be fed back into Grasshopper to continue the parametric process. In certain projects, such as the MX3D bridge, this shape can be run through some sort of a structural analysis, for instance, through Karamba or Millipede to get the stress distribution, the stress line distribution. But sometimes, it can also be something just as simple as a shortest walk calculation between, for instance, some speculative load points at the tip of the shape and the three corners of the base. And you can already see that because of the already irregular shape that we feed in as input, these shortest path simulations already produce interesting axes that go along the shape. Now, from these rather jagged axes, we want to basically consider them as the axis where the mesh needs to densify and thicken and become structural profiles. So the idea is to outline structural regions in between every pair of axes in which we can have a gradient developing. This requires a bunch of technicalities in handling the curves and sorting them and ordering them in the right way to avoid singularities where they used to overlap at a single point. So you can see that now I am able to space them out a little bit from each other to create a non-zero region. And once these axes are correctly sorted and set, there's still a bit jagged, so I can run them through an anemone loop, or it could also be a Python loop to smooth them, while of course still having them constrained to the guide shape. So at first, now you can sort of see these straight lines are going to be the zero reference lines for the eventual profile shapes, where points will be distributed and the vertices will be offset. And the point distribution, the density distribution of the mesh grid is a very interesting step, since we want to create a gradient from an even point distribution to an uneven one. This is namely to produce this visual effect of stretching, where the regions are at their maximum width, and sort of regularity where they're not stretched. In mathematical terms, you could view the point distribution on every row as a geometric series of distances, starting with a certain initial spacing, which is constant throughout the entire column, and gradually growing that spacing with a certain growth coefficient towards the middle. And this already gets a bit complex, but basically this coefficient is iteratively found through a C# script based on the input length, and then it calculates how much this initial spacing should grow in order to fill the length precisely. These distributions, you can see them here. Sometimes they're they already look good, but sometimes they might have a little bit of sharp transitions at the seams. So we can also blur the values of the parameters along the curves, and you can see how a nice grid of the structure develops. And the next step is to turn this zero thickness grid into a double layer mesh that defines the front and the back boundary of the structural skin. And for this, we want to have a harmonic relationship between the density of the grid and the offsets of the vertices for the front and the back layer. So we take the very spacings that defined the density of the grid, and we remap them into offset values, undergoing certain nonlinear warping through graph mappers and modulation through different other parameters, such as the segment girth or the local width of the region. This can influence both the direction of the offset vectors and their amplitude. And an additional modulation can be added to achieve certain specific aesthetic effects. For instance, introducing strategic wrinkling or creases that could add a little bit more detail to the profile. And I do this through the overlap, through the addition of different frequencies of sine waves that control a sort of that add a controlled level of noise to the offsets of the vertices. And you can see what this results in when you combine all these mathematical functions together into vector offsets. This defines the very organically developing skin on the front and the back sides, and the little creases that I mentioned before. Now that we have these front and back layers enclosing this space mesh, as you may call it, we can proceed to generate the opening pattern in the more loose regions of the structure. These openings would serve both to make the skin permeable and to provide connections between the two layers where they come within a certain distance to each other. For this, the topology of the quadrilateral mesh is redefined to extract a diamond pattern from it. Yeah, I hope you can see it. It may be a little bit dark, but these diamond cells would later form the outlines of the apertures of the gradient skin. So we can analyze the distance between every pair of diamonds of the front and the back skin to isolate the regions where the front and the back come within close enough distance. And then within these regions, we create a gradient three-dimensional offset of every cell, which above a certain threshold becomes not just an offset, but an opening itself. And here a specific treatment can be given to the shape of these openings, depending on the type of project. For instance, to avoid certain overhangs in the printing direction. This is a rather simple implementation, but we've had different shapes of these openings for each of the projects I mentioned earlier. And at the very end, all the parts of the mesh are brought back together and undergo a final step of mesh smoothing and through the Weaver-Burks components, which are a very handy tool that always is present in our work. Yeah. So if we have all this process, if we have structured the whole procedural model in a very rigid way, it's assured that when we come back to the very beginning and change an initial input, for instance, change the starting profiles to be squares instead of triangles, everything would more or less smoothly transform into another nice configuration at the end, with a minimum amount of manual tweaking of parameters. So here we see yeah, a tower that is formed by square profiles, and of course the mesh grid doesn't look that nice, but like we can yeah, we can find the right parameter that handles this this issue and densify it so that we have nice results. And so I hope this entire demonstration sheds some light on the process behind some of our works. Yeah, these techniques are by far not the only ones used in our projects, but yeah, they do reflect something of my own personal approach to modeling. And you know, the second half may have been quite fast for some of you, or maybe hopefully interesting for others. But I'm glad to be able to share these techniques because it doesn't come that often that I get to do that. So, and I'm curious to hear how these resonate with other Rhino and Grasshopper users. I hope they maybe inspire some of you. And I would also like to mention, by the way, that this is probably a good point to mention, that we are currently looking to expand our design CAD team with skilled Rhino and Grasshopper individuals. So if this sort of way of working resonates with you, feel free to contact us at info@jorislaarman.com. And with that, I think this is probably, I should leave some time for questions. And yeah, Guillermo, let me know how you would like to proceed.
As you prefer. You have something else to show, we can continue. If not, we have some questions like how were you combining the Grasshopper definition and the Rhino perspective from, I think, from Jordan F.
Oh, you mean how I am able to show
to
both
see
both at the
with the
same time?
transparent Grasshopper.
Yeah, this is actually a trick that I first started using for this presentation, and I find it like really really useful, since my screen is not super huge, so I think it's kind of cool to overlay them too. But essentially, this comes together with a hologram plugin, the AR interaction building plugin. I definitely recommend it, like not just because of this technique, but like because, I mean, should you happen to have a Microsoft HoloLens, but also an iPhone on which it works, like it just has this functionality, and that's you can overlay them in a nice way.
Yeah, it's really nice to have all the screen for Grasshopper.
Yeah, it's too much information that needs to be presented at the same time.
Yeah. No, it's great to see the Grasshopper script bigger and to understand all the components. We were receiving a lot of messages that we had viewers from all around the world, from UK, from USA, South Africa, Colombia, Indonesia. So that's great. And a lot of comments also when you were showing the entire definition that this is quite hard to understand in just a short time. But I think with the recording of the video, we can check it in detail.
Yeah, so I guess my intention was not necessarily to walk you through a very through every component that I have here. I think it's quite intimidating in terms of scale, but maybe some people who have worked more with grasshoppers can sort of like recognize some of the sequences of procedures that they see on the screen. It's an insane amount of stuff that needs to be elaborated on, but for which we would need like a week long course. But I just wanted to be able to provide you a glimpse of the complexity that is behind, like not meant to flex with this spaghetti.
No, it looks very organized and simple to understand with all the names around. And but I think that it also has some C# scripts, so it will be more complex to understand. Because some people is asking if the definition will be available to download. I think it's private for your company, right?
Yeah, I mean, if I guess if there's increasing interest in it, I mean, you're very welcome to contact my studio to maybe there will be an option for creating an educational workshop on it. But of course, a lot of the stuff is related to our work, so it wouldn't be. I mean, we could find a way potentially, but I think I wouldn't also say that this is maybe the ideal way to do things. So I don't want to take this as like the best practice of things. I just I'm just like showing it as an example on how a workflow like this can exist in a practice like ours. But I mean, if you have any if you really want to dive deep into it, like feel free to contact us, and I'm sure we can find a solution to show you more stuff.
Thank you. Yes, I think it's great to see how this process can be made of creating a very simple geometry at the beginning and then transforming in one mesh with some gradients and textures. I think the process is always the same, but then you can change the shape completely.
Yes.
And we have some questions. The webinar will be uploaded to YouTube tomorrow. Let me check because we have many comments that Same. Very nice, very impressive. Thank you for the presentation. Well, this one looks quite interesting from Anton Querez, and I don't know if you know the answer of how do you envision the benefits of Grasshopper 2 for your type of work? Do you think there will be some improvements? I don't know if you have tested it.
Grasshopper 2, yeah. I have to shamefully admit that I haven't been trying it out too much.
It's just an alpha version, so it's
yeah,
not
exactly.
famous developed.
But actually, that kind of sparked my curiosity. I mean, I've been slowly jumping into things like hops and like sort of I mean, trying to work a little bit more fragmented in terms of definition. Obviously, this you know, I'm kind of like I work in a very small team, so we rarely exchange Grasshopper definitions in between us, and that's why something like this can grow to such a monstrous scale. However, if you work in a larger team, of course, it's much smarter and much more efficient to have proper data and version management and like cross-reference between files and stuff, for which I think hops provides a very nice expansion.
Yeah, there are also a lot of improvements in Grasshopper 1 for next Rhino version. But yeah, with some attributes and some more information that you can add to your geometry. So it's not just Grasshopper 2, because Grasshopper 2 is not going to be available soon as a beta version or as a final version. But Grasshopper 1 also has some improvements. Okay, the next question is from Dino, I think. In terms of 3D fabrication process, is there work page that needs to be taken into consideration that, for example, in this project will be post-processes further before fabrication?
I'm sorry, could you repeat the...
Yes. I think it's quite hard for me to read. In terms of 3D fabrication, but I think it's the 3D printing process, is there work page that needs to be taken into consideration that, for example, in this project, I think something wrong here, will be post-processes further before fabrication? So I think it's, if you need to...
For instance, I can imagine maybe what is meant here is like an analysis of overhangs, which are always like an essential part. Yes, in this specific definition, I haven't embedded this as an example, but because obviously it's a project it's not a project that we have produced yet. But usually when we work with MX3D, there's a constant back and forth with them, because on one hand, you know, there has to be a constant analysis of the slope of the shapes towards the printing plane and the printing direction, to make sure, well, actually, it's getting more and more flexible, since the MX3D currently also have an external additional axis which can rotate the piece they print on. But it used to be the case that you know, a lot of times the whole mesh would need to be scanned, and all of its faces, the normals of the faces, need to be compared to a certain reference vector to make sure that they're not sloping too much, so that the material starts dripping when reaching the next layer, and things like that, or perhaps to avoid that certain geometries intersect or come close together in an undesirable way, or have like very long straight sectors that might induce some warping due to the heat expansion of the material. These are all stuff that can be embedded for sure. Yeah. Yeah,
and also how do you split the geometry for 3D printing, right? The different parts, or this is more simple, more manual, depending on the 3D printer?
it depends on the project. So I think well, I think the most interesting one. Well, there were some instances. For instance, the gradient screen. Where no, that's not the gradient screen. Well, where the piece was produced in one go. Sort of, it didn't need to be split at all, so it was all within the reach of the robot arm. Mm-hmm. But for other instances, such as the Nike bench, there were actually specific diagonal seams planned following the diagonal grid, so that they're less noticeable when they're welded together. But also a lot of times it's sufficient to just have a straight cut, because due to the layer structure of the prints, if you have to weld two separate segments together, you're essentially just adding another layer of the same material in between, because it's the same, essentially the same process. The wire arc additive manufacturing, it's literally like welding seams over over each other. So yeah, usually there are certain constraints, such as the maximum reach of the robot, but that's something that very much depends on what kind of machine MX3D are using at the moment, and whether they're using an external axis, which also eases the process significantly. Yeah, and things like that.
Okay, thank you. Thomas Alterman is asking if are the manufacturing robots being controlled by Grasshopper as well?
Well, here I have to say that while I did work close with MX3D during the bridge project, I am technically not part of the company, so I haven't been looking closely at their processes in their latest developments. But I know for sure that Grasshopper plays a very it is still being used, and yeah, plays a very important role. Yeah, I don't know in how far this gets to the actual control of the robots, but for the preparation of the robot G code, I can imagine well it does.
Okay. I'm checking here some more comments. Yeah, a lot of people saying that they want to start with Grasshopper.
Yeah.
And well, we have some question about how did you start it, or how did you start with learn Grasshopper and visual programming?
That's a good one. I think well, it started back in university, essentially, when I was that was probably around more than 10 years ago. Basically my first, I was studying in an architecture school, and basically my first CAD course was Rhino, not even Grasshopper, but Rhino kind of like got me at that time, because it was I had already known a little bit of AutoCAD, and I just saw it as an expansion of AutoCAD's possibilities in 3D, and Grasshopper, essentially I started using it because I felt like it could allow me to have much more expression and like reduce the number of work I put in my projects to make things more smarter. And from that point, I just I don't think I ever even did a course on it, but like it was just basically tutorials and working with other people who knew it, and they showing me the techniques they use, just like working together, just trying out new stuff, looking at other people's definitions. And essentially, once you get the mindset for it, this sort of this visual programming mindset, then it's all about just being able to construct processes and geometries as functions that have like inputs and outputs linked together. And from there on, I think you can learn very easily. I mean, one specific obstacle that took me and probably other people like a lot of time to overcome is maybe the data management of like the trees, Grasshopper trees, and what it means to combine a grafted list with a flattened list, etc. So that's when it gets more abstract, because like, you know, everything else is very visual. You can kind of like redraw the same thing on paper, etc. But data management is something tricky. But like once you get that, then actually the door is open for you to develop further. And there's many courses online and offline that you can take part in. I myself have taught a couple. So yeah, just stay curious and keep trying.
Yeah.
And that's how it goes.
Yeah, I already send some tutorials and courses that they are free, most of them, but there are also some specific courses that you can learn Grasshopper in, I would say, a month or something like that. Mm-hmm. And then, yeah, it's just practicing, and you will learn that you can do something like this in a few years. We have another question that was quite interesting. That is, how do you, or why or how, or if it's necessary to, let me check where was it. If in the case of the bridge, for example, if how do you extract project documentation from your models if it's necessary 2D documentation?
Yeah.
Even if you
I guess
print
this
it.
is well, for the assembly process, well, for the technical drawings, yeah, even there, sometimes you might need, like, if you send it to a welding company that works less with 3D models, even then it might be necessary to have some 2D drawings, and usually that step used to go through just baking stuff in Rhino, make 2D, layouting, etc. So a little bit less automated, but I have the feeling, or at least I haven't tried that lately, but I have the feeling that this is getting a bit more streamlined with the later versions of Grasshopper and Rhino. But I guess it's not it's a bit trickier. You have to like develop your own process of extraction of 2D drawings. It doesn't happen instantaneously.
Yeah. Okay, thank you. Let me check if there is one more here. Yeah, Graham England is asking if are there any good resources for the mathematical expressions you use for creating geometry? You think there?
I would say, I mean, you could start with. I remember there's this one specific PDF tutorial. I forgot the precise name, but it's something like geometric foundations of Grasshopper, or
yeah, I will.
Yeah,
the one from Raya Isa.
Yeah, exactly. Yeah. This is a good starting point. I mean, to get into more and more complex stuff, obviously you need to try to define your problem, break it down into smaller problems, look up solutions for every one of them. Sometimes it helps when you use a ready-made plugin for Grasshopper to sometimes ask yourself, okay, but how does this plugin actually work? And then like go a little bit into the background, maybe go into the forum where there's discussions about this plugin. Maybe you can find links into the more complex algorithms, like when you think about kangaroo or in dynamic relaxation, for instance, like what does that mean? Yeah, it's a kind of a constant search process, and I think that's the most fun part of my job that is bringing most joy, is that you can always learn new things for every project, even if it's an iteration of something you've done before. You can always find new and smarter solutions to do it if you look far enough.
Yeah, I think it's this one that I shared, that is essential mathematics for computational design.
Yeah.
The one you already framed.
Yes, exactly.
Okay, I think just the last few questions. Richard Marina is asking, is there any interest in subtractive approaches or any other material research or interests? You know,
you mean subtractive fabrication approaches or design approaches?
Yeah, I don't know.
Because we do, if it's in terms of manufacturing, we do produce a lot of projects with CNC milling. I think, yeah, like you can mostly the maker series, actually. You can see this is a snapshot of the tool path simulation of a typical milling file of the blocks of a chair that needs to be assembled afterwards. So yeah, that's also
because at the beginning you show a lot of projects with different materials, also with wood and plastics and whatever.
Yeah, exactly.
Okay, and the last one I think is from Ranjit. Is how efficient is the Grasshopper structural analysis? I think you show, for example, Caramba. That is a plugin.
Yeah. Well, I guess what I used in the example was not exactly Caramba, but like it was like a quick. I just like redefined the remeshed. Created an alternative topology of the mesh and did use this shortest walk algorithm, which it's a very simple. Well, I mean, relatively simple, not that sophisticated approach, but it depends on the tool you're using. Yeah, Caramba is very beloved by engineers. Millipede also offers similar functionality when you think about topology optimization and similar stuff. I guess I have tried some of them out. A lot of times it's just that, like, if we use a purely engineering approach, like there's a lot more, I guess, aesthetic driven decisions in our practice that than like structural optimization ones. So we try to kind of find a balance between the two, that the form is somehow structurally intelligent, but also like in a way creates the visual impression that is structurally intelligent, which might not actually be that easy if you use purely like structural simulation or engineering plugins, as controversial as it might seem. But yeah, there's a play of both.
Okay. Thank you. Well, and just the last one is from Carlo. Do you have any plans to expand into architecture, buildings, and similar?
Well, I mean, every now and then we do get projects that handle like larger scales of structures, for instance, pavilions or yeah, larger scale sculptures. We, in a way, it's a little bit outside of the scope of our firm to go into the technical implementation of entire buildings, because we're more about the narrative and the story we want to tell in partly the little bits of innovation that we want to introduce through our ideas. So our projects are more dynamic, more fast-paced, like smaller scales, alternating, changing every once in a while. But we do, when it's about architecture, we usually, our job is more in the conceptual stage, in the more initial design phase.
Perfect, great. Thank you so much, Boyan. The presentation has been amazing, and I think everyone was very happy with it. We were almost 200 people together, so that was very nice. Well, thank you again, and have a nice evening, everyone.
Yeah, it's been a pleasure, and I hope I didn't overwhelm you too much with with the demonstration, but that's why I had the whole first half to sort of have a bit of eye candy so that everybody's happy. But anyway, thank you everyone, and it's been a wonderful time.
Perfect. Have a nice day. Bye bye.
You too. Bye bye.
See you.